we were talking about the Pauli exclusion principle, but I wanted to remind you, or just to back up a little bit, because the Pauli exclusion principle uses this kind of language of two particles being in the same state. And what do we mean? So very early on, when we started talking about section 5.1, we said, if we say particle 1 is in a certain state and particle 2 is in another certain state, the only way to make sense of that statement is if they're in a product state like that, right? We've got a function of the particle 1 variable times a function of the particle 2 variable. In the case of identical bosons and fermions, well, we can't be in such a state because it's got to be symmetrized or anti-symmetrized. So instead we said, well, if you take a state like this, which is a product state, and you symmetrize it, it's not a product state anymore, but we can still consider these cases to be ones where we could say, it's not that particle 1 is in a particular state and particle 2 is in a particular state, but one is in this state and the other one is in this state, and I just can't really tell which. So we can still kind of say that at least one particle is in one state, the other is in the other state, we just don't know which. And then the Pauli exclusion principle, the proof, as we observed at the end of yesterday, is just as simple as saying, if you have identical fermions, you have to have an anti-symmetrized wave function. And that means that these two factors in the one product term can't be the same factor. Okay, so being in the same quantum state means literally those factors are exactly the same. If you do, and you anti-symmetrize it, you get 0. And you can't normalize 0. 0 is not an allowed state, right? We can't have the function 0 as a function of x1 and x2 be an allowed state. Now, what I wanted to kind of focus on, or at least linger on for a while, I don't think that Griffiths says too much about it, is, well, you should think, well, those two states might not be exactly the same state, but they could be really, really close. I could make two Gaussians that almost entirely overlap. So what is the Pauli exclusion principle saying about if I have one particle is in this state, the other one is in a state that, gosh, it's almost exactly the same state, but it's slightly different. So it technically doesn't violate the Pauli exclusion principle. What does it say about that kind of situation? Because we tend to think of, at least for the Pauli exclusion principle, as you think about it in modern physics, we tend to think of like energy eigenstates of the hydrogen atom. So they're not very similar, right? You say, okay, we got the ground state and the first excited state. They don't look almost exactly the same here, but the Pauli exclusion principle isn't saying that these two states have to be different energy eigenstates. They don't have to be orthogonal or anything like that. They're just two different states, and they might happen to almost be the same, have a huge amount of overlap. So let's just investigate that a little bit to see what happens there. So I just want to think about, and we're going to do some worksheet working out of things like this just to be definite. Let's imagine we have identical fermions, right? So they got to be in an anti-symmetrized state. They're non-interacting and they're in an external harmonic oscillator potential. So they're identical, they have the same mass, the classical frequency is the same, but they don't interact with each other. They're just in the same potential well. And they both interact with the potential well. So they're the kind of non-interacting particles we were talking about yesterday. Clearly, if I want to say one is in the ground state, that's this psi 0, and one is in the first excited state, this would be a state that's consistent with that statement, but it's not an allowed state for fermions. I have to anti-symmetrize it. So this would be one where I would say, I'm not sure which one is which, but one of them's in the ground state, one of them's in the first excited state. Okay, that clearly isn't like this, because the ground state is pretty different than the first excited state. So in that case, it would clearly make sense to say one particle is in state psi 0 and the other one's in state psi 1, ground state and first excited state. Here's a case that's more similar to this, but I'm using the harmonic oscillator potential just to make it a little bit more definite and easier to work with than the Gaussian functions. Suppose I say, if they were non-identical, if they were a distinguishable particle, I'm going to put one in the ground state. That's particle 2. It's in the ground state. And particle 1 is going to be in the ground state, but I'm just going to put a tiny bit of the first excited state in there. So they're almost in the same state. I'm imagining epsilon's a really small parameter there. And what I want us to do is anti-symmetrize that and see what happens. I mean, they're not the same state. So Pauli says, okay, that I'm not saying that's forbidden. So let's see what happens when we anti-symmetrize it. And I keep making more and more worksheets associated with this, but what I want us to do is, and if you're on Zoom, this is under today's date on the website. We're doing problem 1A on here, which is to do exactly that. Just anti-symmetrize it, see what happens. I'm putting particles 1 and 2, identical fermions, in almost exactly the same state. If epsilon is really small, then there's a huge amount of overlap because they're both almost in the ground state.
Okay, this is doable. That works.
Okay, maybe you've had enough time to finish it. There's not too much to do. Here's the original state that was given. Particle 2 is in the ground state. Particle 1 is almost all in the ground state, but I've just added in a tiny bit of the first excited state. So they almost have complete overlap in terms of the shape of the function. And that in order to make an allowed identical fermion state, I have to anti-symmetrize. So I've just exchanged again here, X1 stands for X1 and 2 stands for X2. It's just too much writing to put all those subscripts on X's. And let's multiply it out. Well, when I multiply it out, something interesting happens. I have a psi01, psi02 here. And I have a minus psi02, psi01, which is exactly the same. So those terms cancel out. And so what I'm left with is a factor of epsilon psi1, 1, psi02 minus psi 1, 2, psi 0, 1. All of that times epsilon. And then, of course, it's not going to be normalized probably anymore in this case. So I've really got to renormalize. Let me just put a new normalization constant out there. When you anti-symmetrize something, probably going to mess up the normalization. We'll investigate that a little bit later today. And that's kind of interesting. Notice that the very first thing I spoke about was, suppose we wanted to say one particle is in the ground state and one particle is in the first excited state, and we anti-symmetrize it, and we get this. We took this, so this state, they're completely orthogonal states, and when we anti-symmetrize it, we get something. Here, they're not completely orthogonal. In fact, they're almost the same state, and when we anti-symmetrize it, we get exactly the same thing. In other words, the huge admixture of the identical part that we put in there, of course, when you anti-symmetrize, it just goes away. Okay, so amazingly, that symmetric part of it just disappears when you anti-symmetrize, and you're only left with, what properly anti-symmetrizes. So we started with two wildly different, single particle or non-identical particle states, and when we anti-symmetrize them, we get the same thing. So we might say one particle, in this case, it's the same here. We would say one particle is in the ground state, the other's in the first excited state. I don't know which because they're identical, but that's a perfectly legitimate case here. Even though we started out before anti-symmetrizing by putting them almost all in the ground state for both of them, as long as I had a little bit of something else in there, it ended up being completely equivalent to that. Here's another example. I'm starting with, sort of weird admixtures of ground and first excited state. I'm saying particle 1 is in, has lots of the first ground and first excited state in it. Particle 2 also has lots of ground and first excited state. Nothing special about the plus or minus sign here. It's just not necessarily small amounts. And in general, it's anti-symmetrizes to the same state. And what I want you to do in part B of that same problem is, and I didn't put it on the reminder for me to do it here, is actually do the most general case. Let's take an arbitrary admixture of the ground and first excited state for particle 1, and a totally different admixture of the ground and first excited state for particle 2. Anti-symmetrize it, and you'll find out you get exactly the same thing. Up to a normalization constant. So just do it, do a couple of lines and try to convince yourself that the correct cancellations take place. When you anti-symmetrize this sort of beastly arbitrary admixture of ground and first excited states for both particle 1 and particle 2. Oh, and I see a typo in there. The term D should have an x2 as the argument with the D coefficient. That was me copying and pasting. In other words, the two terms in the first parentheses are x1 variables. The two terms in the second one are supposed to be x2 variables, but the D term didn't quite show up there. It's supposed to be an x2 right here. That's a typo in the worksheet.
It also has sides.
Oh, then that explains, I just clicked on something and corrected the wrong thing. Yes, so that should be a psi 1. I think what I've got written up here is correct. Clearly, I edited the subscript on the wrong thing when I was copying and pasting there. I changed I did change a 1 to a 2, but it was the wrong one being changed to a 2. Yeah, so what's written on the board now is the correct. Let's see if I can focus that any better. Okay, not too, in terms of the mechanics of this, not too much profound is going on, but you can save yourself a little bit of work if you just sort of mentally look at what's going to cancel out. If I look at in this first product here, so I'm anti-symmetrizing, this is what was given. I'm anti-symmetrizing over there with just by exchanging the 1 and the 2 arguments. In this product, anytime I have the subscripts on the sides agreeing, in other words, here I have an A, C, psi 0, 1, psi 0, 2. I'm also going to have a minus AC, psi 0, 1, psi 0, 2, which is going to cancel it, right? So the first ones here cancel with the first ones over there. The last ones here cancel with the last ones over there. So that gets rid of a lot of the terms, which I'd prefer not to write down just to save a little bit of writing. That means I've got to do the outer and inner to keep track of things. So let's see, we've got an AD here, psi 0, 1, psi 1, 2. Let's look at the corresponding term over here. I've got a minus AD times psi 0, 2, psi 1, 1. So minus that same AD times psi 0, 2, psi 1, 1. A similar thing happens with the BC term, right? Here I've got a BC times psi 0, psi 1, 1, psi 0, 2. I better write it down or I'm going to get confused, right? So I've also got a plus BC psi 0, 2, psi 1, 1. And then over here, I've got a minus BC psi 0, 1, psi 1, 2. So many numbers, it's hard for me to keep track of. And notice that these are almost the same things. They're actually the negative of each other. So if I put a minus sign here, then I can turn this exactly into this. And maybe I'll just indicate that by saying we've got the exact same thing in those parentheses as we do above, as long as I put a minus sign there. So amazingly, after all of this is said and done, I get AD minus BC times that same combination, psi 0, 1, psi 1, 2, minus psi 0, 2, psi 1, 1. And then, of course, I got to renormalize it. So I probably just put an arbitrary normalization constant out in front of it, but it's the same state. That's amazing. No matter what combination of the ground and first excited state I take, when I anti-symmetrize it, I'm going to get, there's only one thing to get. As long as I got some tiny bit of each one, it just, all of it goes away and we get the same admixture. To me, that's kind of counterintuitive. So here was just one particular admixture that I was taking, but we just showed it's true in general. It doesn't matter what admixture of psi 0 and psi 1. Now you might think, well, okay, that's special because in this case, these happen to be orthogonal states. So maybe it has something to do with the orthogonality, but actually it doesn't have anything to do with the orthogonality. Okay, so we tend to think of the exclusion principle as applying, at least the way you learned it in modern physics, we tend to think of it as having to do with energy eigenstates, because we're sort of thinking up of building atoms with multiple electrons in it and saying the electrons can't be in the same orbitals, the same energy eigenstates. But in fact, any two factors they don't have to be orthogonal. They don't have to be energy eigenstates for the Pauli principle to apply. And the proof didn't assume anything about them being energy eigenstates, and it didn't assume they were orthogonal states like the case we were doing here at all. So let's try just a random one, right? So let's say, okay, we're still talking about the harmonic oscillator potential. Here's a random Gaussian. It's not an energy eigenstate. Here's another random Gaussian. The only difference is they're centered at different values. One's centered at x equals a, the other one's centered at x equals b. We'll call those state A and state B. And let's place one particle in state A, the other particle in state B, and anti-symmetrize. Okay, so here's particle 1 in state A, particle 2 in state B. A and B might be really close to each other. A and B can't be the same value, otherwise it will anti-symmetrize to 0. So if we take this and anti-symmetrize it, if we take almost all of A for both particles, but just a little bit of B for particle 1, right? So they're almost the same state. It will anti-symmetrize to the same state. It's just psi A1, psi B2 minus psi A2, psi B1. It anti-symmetrizes to it. Similarly, if I take any other linear combination of A and B for particles 1 and 2. This is, again, it's just, there's nothing special about this state. This is just one kind of randomly chosen linear combination with nothing special about it. It anti-symmetrizes to exactly the same state. So as long as we've got a little bit of something different in there, we would probably be tempted to say, again, doesn't matter which one of these states we anti-symmetrize, but all of them could be characterized by saying one particle is in state A, the other particle is in state B. Even that's a little bit kind of overreaching to state things that way, because notice, here's a different state, right? In this third case, this is not state A. We're saying particle 1 is in A plus B. Particle 2 is in A minus B. So why wouldn't I say particle 1 is in state psi A plus psi B, and particle 2 is in the difference of those two states? So maybe a more accurate way, I'm not sure exactly the best way to state it in the least misleading manner, but we could say particles 1 and 2 are in an anti-symmetric combination of those states. Lots of different states form the same anti-symmetric combination. So we shouldn't take too literally the states A and B there. It's kind of like saying, well, if I have x hat and y hat, they span a two-dimensional vector space. But maybe so do W1 and W2, which aren't even orthogonal to each other. And would I say a vector is an admixture of x hat and y hat, or W1 and W2? It doesn't matter. They're both the same. If they're an admixture of those two, it doesn't matter which basis set I'm using. Okay, so that's just to elaborate a little bit on the Pauli exclusion principle and say, even though we tend to think of orthogonal energy eigenstates, the idea is they don't have to be orthogonal. They can be almost the same state. All that really has to be true is that they're not exactly identical states that the two particles are in. All right, we've sort of already talked about this, but let's just visualize a little bit of what these identical boson and fermion wave functions look like, and let's contrast it with the distinguishable particle case, right? We said that the wave function for a distinguishable particles 1 and 2 can have any normalizable shape. So I'm imagining here, in the x1, x2 plane corresponding to where you measure particle 1 and particle 2, I could have, as long as this is a normalizable function, again, I'm drawing level curves here. It doesn't have to have any special symmetry. It can be, place lumps wherever you want in that plane. As opposed to identical bosons, once you symmetrize it, it's got to be exactly symmetric with respect to reflection over the line x1 equals x2. So it's symmetric with respect to that line. And similarly, when we anti-symmetrize, we get a function which is exactly anti-symmetric with respect to the line x1 equals x2. Whatever it's doing right here, it's doing the opposite of it right there, right? If it's negative here, it's going to be positive here. If it's positive here, it's going to be the corresponding negative number over there. And because of that, because of anti-symmetry, that means it's got to be 0 along the line x1 equals x2. And you can almost think of that as being, telling us something about the Pauli exclusion principle. We're saying, if it's in a state and I measure the position of, suppose I measure the position of particle 1 and I find 3. So x1 is 3. What's the probability if I measure x2 that it's going to be 3? And the answer is 0. Because the probability density has to be 0 along this line. Since the wave function's value is 0, when I take the magnitude squared, I get probability density of 0. And so the Pauli exclusion principle, of course, one version of it says, if particle 1 is in the state x equals 3, particle 2 can't be in the state x equals 3. So if I measure the positions of the particles, they shouldn't both have the same values. Once I measure those positions, I'm forcing them into definite states of definite position. The Pauli exclusion principle says they can't be the same. All right, we looked at these pictures before, but again, this is just emphasizing the symmetry. No special symmetry for distinguishable particles. You can have lumps and bumps wherever you want as long as it's normalizable. But when you symmetrize, it's got to be completely symmetric with respect to this line. This is the x1 equals x2 line going straight down the middle here. Again, the origin is there. x1's going along that direction, x2 along that direction. So here we have symmetry, and here we have anti-symmetry, which forces the function's value to be 0 along that line. And that has practical consequences. What it means is that, when you symmetrize, you tend to put more probability in the middle along the x1 equals x2 region. And when you anti-symmetrize, you tend to push those peaks further away from the line x1 equals x2. And that it relates to something that Griffiths covers in this section that's entitled exchange forces, which is a little bit misleading. As he says, they're not actually forces in any usual sense, but when you have bosons around, they tend to be found closer together. So it's as if there's a force pulling them together just because of this symmetrization. And when you have identical fermions around, they tend to be found further apart, as if there's a force holding them apart. People call that exchange force, even though it's not a force. It's not the gradient of a negative gradient of a potential energy function. So it's not a force in a traditional sense. It sort of that makes them act as if they repel each other. So that's why people call it an exchange force. So let's imagine two different states. So here there's one state that a particle can be in, psi A, the other one, psi B. Maybe they're very similar. We're going to assume they're normalized states in the calculation that follows. I'm not going to assume that they're orthogonal here. They could be almost the same state, at least for the time being, although we'll make that assumption a little bit later to simplify things. So if particle 1 is in state A and particle 2 is in state B, which certainly can be the case for distinguishable particles, they're in a product state. If there are identical bosons, they can't be in that product state. The closest thing is to say, well, one's in state A and one's in state B, and I can't tell which. That's the symmetrized version. Once we symmetrize, even though these particles, these individual states are normalized, this symmetric combination won't be normalized, and I'm going to need to figure out what that A is. Similarly, if I form the anti-symmetric combination, it's not going to be normalized anymore, and I need to find out a normalization constant for that. And it's sort of interesting to see what that normalization constant has to be, and that has to do with, I think, the same no. This was the worksheet. Gosh, I've got so many worksheets here. I don't know that I have a copy of the one. This is the one we used yesterday in class, not the one that has the axes on it, but what is on it? I don't have a copy of it here. We did part of it. On the front was that case where we were counting the degeneracy of the harmonic oscillator states, and that. We're now on the back side of that sheet, and the idea is let's assume that these states are normalized, and we're going to form an anti-symmetric combination of them, and I want to just see what that normalization constant has to be. And in A, I'm asking you to guess what the normalization constant is without doing the work. And then in B, we're actually going to do the work and see if we can figure out what the normalization constant has to be. And the work is a little bit complicated, so maybe we can go through it together at the board. All right. So what do you guys think about if you had a guess for the normalization constant A, if these two states are normalized? So psi A and psi B are individually normalized states, and then we take this particular combination. Do you have a guess for what the value of A would be? 1 over root 2. I would have guessed that too. It seems like it. It turns out that guess is wrong, but that's a reasonable guess that a lot of people make. The reason it's wrong is because we're not assuming that these states are orthogonal. You would be correct exactly if these two states, psi A and psi B, were orthogonal. But because they're not orthogonal, in other words, because they could represent two Gaussians that almost completely overlap, when we anti-symmetrize, almost all of it disappears. And we're left with a function with a very small amplitude. And then we got to have a huge normalization constant to make the area under the curve of rho be 1 again. So let's work it out on the board. It's a little bit of a pain. I will show the board in just a second. I'm doing all this stuff because when I first encountered these were all questions that I had, and oftentimes I was thinking of things in the wrong way. And, I would think, oh, that constant's got to be root 2, 1 over root 2. Why isn't the book stating it that way? And okay, so let's calculate let's find the area under the curve. So my state is, my big psi is going to be psi A of x1, psi B, oops, this is am I calling it capital size? Yeah, capital psi A, capital psi B of 2 minus psi b of 1, psi a of 2, all of that, and I want to put an a out in front. I'm just calling this the, I don't know, we'll call it psi f for fermions or something like that. And now what I want to demand is that when I integrate over all x1s and all x2s, x1 from minus infinity to infinity, x2 from minus infinity to infinity, what do I have? I need the magnitude squared of this. I'm going to demand that it's equal to 1, right? When I take the magnitude squared of it, we'll assume a is a real normalization constant. So magnitude squared, I'll leave the magnitude off the a, but now I've got to take the magnitude squared of this, which is psi a1 star psi b2 star minus psi b1 star psi a2 star. Okay, we're doing psi star psi. So here's the psi star. I've got to multiply that times psi. Psi a1 psi b2 minus psi b1 psi a2. Very easy to make a mistake when you're doing this. And then I'm going to integrate over all x1 and x2. And I'm going to demand that that equals 1 somewhere right way down the line. And let's just take this, you know, I've got to distribute this out or FOIL it out. If you speak the language of FOIL. So let's see, let's take the first times the first, right? So this first terms. I'm going to get psi star a1 times psi a1, and that's going to be integrated from x1 equals minus infinity to infinity, right? And that's going to give 1, right? So when I integrate from minus infinity to infinity of psi a star 1 times psi a1, and we're assuming that's a normalized function, when we integrate it from minus infinity, we get 1. So this is, I'm just continuing on down here. I have a squared, and then I'm going to have 4 terms. We're going to do the first ones first. I'm going to get a 1 from the x1 integral. And I'm going to get a 1 from the x2 integral, because I'm going to get psi b star of x2 times psi b of x2, which integrates to 1 when I integrate over all x2. So I get a 1 times 1 there. How about the last? I get a psi b, let's see, both these have minus signs, so they multiply together to give a 1. I get psi b star of 1 times psi b of 1, integrated from minus infinity to infinity, so I get another plus 1. And the second factor gives a 1 also in the same way. So this is my first terms, this is the last terms in terms of foiling it out, if you ever used that language. And then I've got to do the outer and the inner. So let's do outer now, okay? I've got, this one's going to be a little bit more complicated and not so easy to work out. In terms of state 1, or sorry, variable 1, I have a minus psi a star 1 psi b 1 integrated from minus infinity to infinity dx1 times the 2 integral gives a, sorry, I'm doing this one. The 2 integral is a psi b of 2 psi, and that's starred, times psi a of 2 integrated over all x2 from minus infinity to infinity. Okay. And then when I do the inner functions, I get something very similar. When I do the inner functions, I'm going to get, let's see, psi b star times psi a, integral of psi b star psi a times the integral of psi a star times psi b. I'm being increasingly cryptic. This is these are of the same variable. You're integrating the variable from minus infinity to infinity. I'm leaving off the dx just because I'm getting tired of writing all this stuff, right? Okay. I think that's, so this is the outer terms and this is the inner terms. And now I've got to think about those. Let's define, or at least in my notes here to simplify, I said, let's define this integral, the integral of psi a star times psi b. Whatever this integral is right here, it's got some complex value because those functions might be complex. And I'm not taking the magnitude squared of something as the argument, so it could be a complex result. It's some value c. Would everyone agree that the value of this integral, whatever that value is, this is going to be c star? Because everything I'm integrating is just the star of what it was over here, right? Here I've got a psi b, here I've got a psi b star. Here I've got a psi a star, here I've got a psi a. So the whole integrand is just complex conjugated. And when you integrate a complex conjugated integrand, you just get the complex conjugate of the results because you're everywhere you're adding up a minus bi's instead of a plus bi's or something like that, right? Similarly, down here, let's see, the a star b, so this would be a c. This integral is what I'm calling c. This integral is what I'm calling c star. Okay, so let's just try to put it all together. I have a 2, so this is a squared times a 2, that's my 1 plus 1. And then I have a minus 2 c times c star, right? Okay, and we're going to demand that equals 1. And therefore, the appropriate normalization constant for this, let's just put it up here. Our fermionic wave function, which is now normalized, the appropriate normalization constant is 1 over the square root, or 1 over the square root of 2 times 1 minus cc star. Okay, where c is this mess. And now we've got to think about, well, what is that? When is that normalization constant going to be big and when is it going to be small? That's what's being elicited in the next part. So I've now normalized it. Just it's a little bit of a mess because it's expressed in terms of this, unfamiliar integral. But if I could figure out what that integral's value is, then I've normalized it. And now let's think about the answers to C, D, and E in here. In what cases will the normalization constant be 1 over root 2, which most people guess? That would have been my original guess without thinking about it too much. When is it going to be just 1 over root 2? Well, that's when C is 0, because then C star would, it doesn't matter what C star is, but if C is 0, then it's going to be 1 over root 2. What's going to make C 0? How would you characterize what the relationship between psi A and psi B is there? If they're orthogonal, right? If this integral is 0, that means state A is orthogonal to state B. So the answer to C on there, that question is, they'll just be good old 1 over root 2 if they're orthogonal. But if they're not orthogonal, it won't be a 1 over root 2. It's going to be something generally bigger than 1 over root 2, right? Because C, when you take a complex number and you multiply by its complex conjugate, you get a non-negative real number. So this is going to be something positive, which is going to make this smaller, which is going to make the overall normalization constant bigger. That's because you're getting some cancellation between where they overlap, right? And so let's see, what does it say in D? In what cases will this state be non-normalizable? Well, it's going to be non-normalizable in the case where if this normalization constant, well, if the thing in the denominator goes to 0, then I need an infinite normalization constant, right? So if CC star is equal to 1, in other words, if the magnitude of C is equal to 1, when is the magnitude of C going to be equal to 1? Well, certainly that's going to happen if psi A and psi B are the same state. If they're the same state, then what I'm doing is just asserting that the fact that if they're the same state and they're normalized, then this integral is going to be equal to 1. So if they're the same state, I need an infinite normalization constant. That means when you anti-symmetrize, it goes to 0, and there's no way to bump it back up again by any finite normalization constant. Are other normalization constants possible? Yes, anything in between those two, right? It could be as small as 1/√2, but it could be any number between there and infinity, depending on how much overlap there is between these functions that we're talking about there, psi A and psi B. So those normalization constants can be, pretty big. And I'm just, again, trying to flesh out some of the stuff that's left out of the discussion of the exchange force and Pauli exclusion principle information. So these A's really depend on exactly whether these functions are orthogonal or exactly how non-orthogonal they are. The less orthogonal they are, the bigger the A is going to be that's required to normalize them again. I'm now going to, just to be definite, I'm going to follow the work of Griffiths here, and we're going to, get into more messes. If they're not orthogonal, things turn into a huge mess. So we're now going to assume that these two states are not only individually normalized, but they're orthogonal states. So it's like the ground state of the harmonic oscillator and the first excited state or something like that. Orthonormal states. And here's what Griffiths says we're going to do to try to get an idea of, on average, how far separated are particles 1 and 2 if we measure their positions. So what we're going to do is form x1 minus x2. That's how far between x1 and x2. And if we take the square of that, that throws away any minus signs, because if we didn't take the square of it, then when we take the expectation value, you're averaging a bunch of positive numbers and a bunch of negative numbers. You'd expect 0. It wouldn't tell you much. But if you square it, you're throwing away any minus signs. And so we're averaging a bunch of positive numbers. And the bigger this expectation value is, the more likely the particles are to be measured far apart. Okay, so this is going to be a measure of how far apart the particles are likely to be found. And we're going to find out that if they're fermions, they're likely to be found much farther apart than if they're identical bosons. And the case of distinguishable particles is going to be in the middle. Okay, you can just square out this thing inside there, right? I'm just going to square it out. I'm going to get an x1 squared. I'll get a plus x2 squared. And if you observe, you got to think about it for a second, the operators x1 and x2 actually commute with each other. So I'm going to get a minus 2x1 x2, a minus x1 x2 and a minus x2 x1, but I can convert them into the same form because those operators commute with each other. One way to think about that is, just like x, the operator in the position representation, that is the operation of x, is you just multiply by the variable x, right? So I have x1 and x2. The operation of x1, the operator acting, is just to multiply by x1. And the operator of x2 acting is just to multiply by x2. It doesn't matter which way I write those variables. Variable x1 times x2 is the same as variable x2 times x1. So they commute, and so I can combine them together in this form. And now what we're going to do is calculate this expectation value by taking each one of these three terms one at a time for the distinguishable case, and then we're going to take Griffith's word for it on the identical bosons and identical fermions case. It's not too bad. He works it out in the book, but we'll work it out in this case. So what I want to do is have you, just because it's tempting to gloss over this when you're reading the book, Griffith says, if the particles are distinguishable, if they're in this state up here, we don't need to symmetrize or anti-symmetrize. And again, we're assuming they're normalized and orthogonal individual states, that this simplifies down to the expectation value of x squared, right, the x squared operator for a single particle in state A, plus the expectation value of x squared for a single particle in state B. So the little subscript is referring to what state you're calculating the expectation value in. Minus 2 times the expectation value of x in state A times the expectation value of x in state B. So let's work that out. That's the second problem on the worksheet I just handed out today, or the one that's under today's, what I've written up there looks sort of trivial, but you've got to think about what the right-hand side means and convince yourself of that. So we're assuming they're in this distinguishable state up here. The two particles are not identical, and we're assuming these are normalized and orthogonal states, A and B. So they're, and we're going to use that in simplifying this. Calculate this thing up here and show that it reduces to this case down here. It almost looks trivial, but you've really got to think about those symbols to, it's not completely trivial, I should say. Maybe I'll write the problem up here. If you're having trouble getting started, either because it looks so trivial, the statement of it, or you've just forgotten, what is an expectation? Here's the state we're in, and we're saying calculate this expectation value. And when we calculate an expectation value, that means you sandwich, sorry, this should be a square there. Sandwich the operator you're taking the expectation value between psi star and psi, and then integrate over all values of the variable. So here we got to integrate from x1 from minus infinity to infinity, x2 from minus infinity to infinity. So this is just the first term here, right? And then we want to see if it simplifies down to the expectation value of x squared in state A. Okay, and then I've got some other stuff I've got to add on here. Okay, so here's the three terms we need to calculate, right? And this is literally what the first step was. And now we're saying, let's calculate this expectation value. Here it is. That's my state. Put that star, operator, that, and integrate. Same thing for this one. I put an x2 between there. And the third one, I put an x1, x2, and I've got that -2 out in front. And now I just have to look at the individual things, right? I'm going to say that in this case, I've only got an x1 in here. So in terms of the x2 integral, I've got an integral of b star b of x2 over all x2s, which gives 1, right? So this, just this first term gives a 1 for the x2 integral. And then the x1 integral is saying, if I'm in state A, it's the expectation value of x squared for a particle in state A. I don't have to worry about the, I labeled the variable x1 here, but we just as well could label it as x. Forget about the other particle. It's just one particle in state A and find the expectation value of x squared. This second term, I get a 1 from the the 1 integral, right? Because this is an x2 here. So in terms of the x1 integral, I just have a psi a star psi a, that gives a 1. And then the remaining thing is the expectation value of x squared when you're in state B, right? Because x2 squared is sandwiched between a psi b star and a psi b, and we have to integrate, and that by definition is what that expectation value is. And here I can separate the x1 into the 1 integral and the x2 into a separate x2 integral, and we get, here we still have the -2 out in front, and it's the expectation value of x in state A times the expectation value of x in state B. It almost looks like the same thing as what we started with, but you really got to think about it to show that to yourself. Okay, so this is the claim. If the particles are distinguishable, it reduces down to this. That's not a particularly interesting result, but we're going to compare it to the indistinguishable case where we have identical fermions or bosons. If we want to do the case of identical, say, bosons, I've got to add, make this symmetrized. If we're talking about identical bosons. Then this turns into kind of a mess, right? When I want to calculate this thing, instead of just having this here, I've got to have the symmetrized version. And instead of having this here, I've got to have the symmetrized version, or for fermions, the anti-symmetrized version. So I got lots of terms, and it turns into a huge mess. But you can use the fact that they're orthogonal to each other. That makes some terms go to 0. And the fact that they're normalized, that makes some of them be 1. You just got to think through it piece by piece. And Griffiths works through the details in enough different cases that you can follow it through if you take out a sheet of paper and remember the fact that they're orthogonal and normalized. In the case of identical bosons or fermions, so now we're talking about a state that looks like this. And again, we're assuming they're orthogonal, so the appropriate A would be a 1/√2 in this case up there. You get exactly the same result, but with some extra terms added on to it. There's a minus sign for bosons, and there's a plus sign for fermions, times 2, times some integral magnitude squared, and the integral is down here. Okay, and that's an integral that without knowing anything about the states individually, it's hard to know what that integral's value is, but it has some value. we're taking the magnitude squared of it over here. So that means the 2 times the magnitude squared is a positive number. Right? When you take the magnitude squared of something, it's definitely non-negative, right? So this 2 times the magnitude squared is a positive number. So that means compared to the distinguishable case, for bosons, we're subtracting off something. And for fermions, we're adding on some positive value. So that means comparing distinguishable to identical bosons or fermions, the bosons have the smallest value for this, and the identical fermions have the largest value for this. And remember, this is kind of a measure of, on average, how far apart are the particles going to be found, right? Because if x1 and x2 are wildly different, then this is going to be a big positive number. And if they're almost the same, this would be a small positive number. We're averaging those together for all the possibilities. And so to summarize, if we just call this big mess up here, we'll call this delta x squared. So the expectation value of delta x squared is the distinguishable case for that minus or plus some positive value, where the upper index corresponds to bosons, the lower one for fermions. And that means on average, the distinguishable case is, sort of the middle case, and then bosons are likely to be found closer together because this measure of average separations is going to be smaller, and fermions are more likely to be found farther apart. So that's one way to sort of put the numbers to it. At least in the case that, Griffiths, again, is showing this in the case where we're talking about orthogonal states. If they're not orthogonal, this becomes even more of a mess. I've tried to work it out, and it just turns into kind of a nightmare. So it's reasonable that he's assuming they're orthogonal. Okay, so again, this effect that bosons tend to be found farther apart is almost as if they repel each other. They don't like to be at the same place. There's 0 probability of them being found together. And on average, when you measure their positions, they tend to be farther apart compared to distinguishable particles, and bosons closer together. So that's called an exchange force. Even though it's not a force in the traditional sense, I think I say that it's not a force at all. It's not associated with a potential energy. All real legitimate forces are associated with some potential energy function. You take the negative gradient of it to get the force. It's just sort of a statistical comparison with the non-identical cases. So, we're just being sort of fanciful in calling it a force. There's no force there, but they tend to be found farther apart. Notice that this last term can get really close to 0 if state psi A is non-zero in places only where psi B is close to 0. In other words, if there's almost no overlap between these states, so where psi A is non-zero is in only locations where psi B is close to being 0 and vice versa, then the product is going to be very close to 0 everywhere, and this additional term will be very close to 0. And that means that if the particles are well separated, their wave functions are well separated for the 2 states, then it doesn't really matter if you symmetrize or anti-symmetrize or just leave it as the distinguishable case. The average separation is going to be about the same. And so Griffiths makes the statement that, if one electron is in Chicago and the other one's in Seattle, and you're doing any sort of normal experiment, you don't have to worry about anti-symmetrizing those 2 states. Or the worst case scenario is, technically, I'm supposed to anti-symmetrize all the electrons in the entire universe, right? I don't know the difference between them. And so when I measure an electron in Chicago, well, it might have been the other one that was in Seattle, and I really should be doing everything all at once. Clearly, that doesn't work. This is a demonstration that, that if you have wave functions that have almost no overlap, in other words, when one is non-zero, the other one's approximately 0 and vice versa, then you are actually going to get all the same experimental results if you don't symmetrize them as if you do symmetrize them. So, if I have an electron here in the lab and there are no other electrons nearby, I don't have to worry about symmetrizing with other electrons that are far away. I can just say, oh, let's just pretend there's just this one electron. I don't have to worry about all the other ones in the universe. Okay. And again, on average, this is sort of saying when you symmetrize, this would be an allowed state for non-identical particles, for distinguishable particles. This one over here would be an allowed, the corresponding symmetrized state. On average, you're seeing more stuff close to that center line. And that's what's making the particles more likely to be found together. Whereas the fact that when you anti-symmetrize, you get 0 along that center line makes it so that the regions in which it's most likely to be found are farther away from that center line. And that makes that average separation larger for fermions. All right.